Hey everybody, it's Dan, the Git School Dude here, once again with another Git tutorial video. Today's video is a little bit different. It contains a few lectures of my Udemy course titled Fundamentals of Git Source Control Management. This course is a succinct introduction to the basics of Git with a focus on understanding core concepts, specifically tailored for visual learners like myself. It's perfect for someone completely new to Git, but also great for intermediate Git users that occasionally run into trouble. Anywho, over the last few years, I've had modest subscriber growth and some great conversations in the comments, so I wanted to give back to the YouTube community not only by open sourcing a significant portion of the course in this video, but I've also enabled a few coupon codes that allow me to give the course away for free for a few days after the video premieres. Check the video description for all coupon codes. Now onto the course preview, which contains 5 out of 22 of the total lectures in the course. Enjoy! Okay, now that we've covered some of the basic commands that you'll be seeing in Git, I want to take some time to back up, pump the brakes, and really just show you the foundation of why we have source control management, and this will lead directly into how commits in the repository are defined. So as we mentioned before, Git will track whatever you tell it to track, and normally this is ASCII text, this is code, this is input to your program. These are scripts that are associated with testing. It could be a lot of different things, but typically it's ASCII text, and what's nice about that is that it will compress well. So under the hood with Git, it's tracking every state of every file, and it does compression on those files. So when those files are ASCII text, they compress well, which is nice. Now, the terminology associated with the files at a particular state is kind of all over the place. So I'll say different things. You'll see it in different tutorials. A lot of people call it the workspace or the working tree. I've also seen working directory, or literally people just saying files on disk. This is just to distinguish that these are the files you care about, the ones you're working with, not the hidden .git internal files. So in the next few slides, I'm going to walk you through a visualization of how save states are created. And I don't know about you, but I'm a visual learner, so when I can actually see things visually and how it progresses over time, it really helps me understand how a system works. So in this example, we're going to use 2 scripts here. This is just a Python script called myscript and a C++ file called a.cpp. And we're going to create a new Git repository with just these 2 simple files in it. When we create our repo and we make our first commit, we're basically telling Git to save the state of my files. And in this particular case, we have 2 files, and we are going to visualize that state, the first save state, as a single circle. And this circle simply represents the exact state of this file and this file. It might seem a little weird at first, until we start making other states. So let's say we change these 2 files. We change this buddy thing to say guy, and we change the cout for hello world to say hey there, and then we create a second save. So as time progresses, we're going to add files, we're going to remove them, maybe files get renamed over time. All kinds of things can happen in the repository, but regardless of what we as a developer choose to do or what anyone else using our repository chooses to do, we can always visualize a particular state of code as a saved state of files. So we've already seen the first save and the second save. In the third save, we've added a file. In the fourth save, we've subtracted a file. In the fifth save, we're back to, I think, the second save. Over time, the files will change, but we can always visualize them as a circle linked to a set of files, and that's what's important here. So it may not immediately be apparent, but each one of these save states actually has an invisible relationship to the state before it. So for example, the 5th save was built from the 4th save's state, and the 4th save state was built on top of the 3rd save state, and so on all the way down to the 1st save. And we can actually represent this parental relationship visually using arrows, which I've done here with these red arrows. It just says that the parent of the 5th save is actually the 4th save, the parent of the 4th is the 3rd, and so on all the way down to the 1st save. Now the 1st save is actually the only save state that has no parent, and that's because we created the repository at that state. In Git, this is known as the root commit. In other words, the very first commit that was created when the repository was born. Now you may have already noticed that it's pretty cumbersome to visualize all the file states for every save, and in this example we only have a handful of files. Real repositories can have thousands of files. So typically we just draw the circles representing those save states and the parental relationships. The arrows that we had before are actually unnecessary too, since by convention we have decided that newer commits are at the top and older commits are at the bottom. So by definition, the fourth save is the parent of the fifth save because the fifth save is above it, drawn visually in this way. I hope that makes sense. What we've drawn here with these save states, and we're not showing the files because it's too cumbersome, but we know that they're there. This is actually the foundation of all source control management. The creation of these save states and the ability to retrieve them over time is the entire purpose of SCM. And in Git, these save states are known as commits. And we've already mentioned this before. So I just replaced the save here with commit, and we can see that we have 5 commits in this example Git repository. Now, different source control management tools actually choose different ways to label these states. Instead of numbering the commits, Git has chosen a unique identifier that we already mentioned known as this SHA-1 hash. So this is actually a unique 40-digit hexadecimal number. And one thing that's cool about it is that it can always be generated from the content of the commit itself. So just to update our visualization here, instead of labeling this first, second, all the way through 5th commit, we're going to label them with the actual 40-digit hexadecimal SHA-1 hash associated with those states. Along the same lines of reducing cumbersome notation, this full 40-digit representation can also be difficult to manage when we're trying to display things. So commits are often shown with just the first few characters of this 40-digit SHA-1 identifier. Now, in Git terminology, you can typically reference just the first few digits, and Git will understand that you mean the full representation of it. Now, if you're new to Git, this may seem a little bit confusing. Why would Git choose to label their commits in this way instead of just a normal numbering scheme like we've seen in older version control tools? Well, there's a handful of reasons, and they're good reasons. One, simply numbering the commits like we did before, where this was 1, 2, 3, 4, and 5. That will break down when there's more than one branch. And so we're going to talk about branches here soon, but just be aware that, when branches happen, well, what do you do? 1.1, 1.2. So no matter what, you're going to have a more complicated way to represent commit notation in any version control system that actually supports branching. So in addition to reason number 1, we rarely need to actually remember these commit SHA-1 numbers, so the complexity associated with it really isn't an issue, and you'll see that in practice when we do these examples. And the third reason, and is the most powerful reason in my opinion, is these hash identifiers actually are generated from the content of the commit itself, which actually allows Git to have some type of repo self-verification mechanisms. So there's not enough time in this course to get into the details associated with that, but just be aware that there's good reasons for having this 40-digit SHA-1 hash identifier associated with particular commit states. So if we bring the file states back in here just for this demonstration here, I just want to point out that in a normal Git repository, the workspace, which is also called the working tree, can only be checked out to a single commit at a time. That makes sense, right? You're only going to be working on one state of code at once. Now you can switch between states at any time, but you can only see one state of code at any particular time. And the commit that you're currently checked out to is known in Git as head, all capitals. And when you run the git log command, it will always show the head commit at the top. That's why it's called head. So for example, if we ran the command git checkout 8557b36, that will put head here at this exact location with these file states in the workspace. Okay, so a little bit more on commits here. So we've already talked about this, but I really want to emphasize that when you make a commit, it's actually a local action. We have no interaction with the remote. We're simply adding a save state to our local repository. Of course, they are uniquely identified by this SHA-1 identifier, and it's important to note that every single commit represents more than one thing. Of course, it's an always retrievable exact state of code that we can always check out to. We could git check out to this state, git check out to this state, and so on. But it also represents a difference from its parent or parents. So you can see over here on the right that we have 3 commits, and the second commit's the parent of the third, and the first commit's the parent of the second. Like I said before, except for the first commit, all commits have at least one parent commit, and typically the parental relationship is shown with time increasing bottom to top. So newer commits are on the top, older commits are on the bottom. And in this example on the right, since every single commit has one parent, we call these linear commits. In Git, a merge commit is simply a commit that has two parents instead of one. Now, I say star here because it's technically possible to have more than two, but 99.9% of the people that use Git only ever have two parents at once, so we're not going to talk about the more advanced cases where you have more than two parents. And in Git, a merge commit is created when one commit merges with another of divergent history. So you can see here on the right, we have a divergence in history. At some point, someone created the 798 commit, and then they created the A36 commit. And then at some point, two commits were created off of that, meaning the code changed to become 63A, but it changed a different way to become 8A4. This, might be an example where two coworkers are working off the same state of A36. They do two different things, and they get two different commits out of it. The code can diverge for as many commits as you want, but at some point, if you want to merge the changes back in, you have to create a merge commit. This is of course done with the git merge command, and I'll show you some examples of that here in the upcoming exercises. But right now, it's important to understand that merge commits represent two sets of differences, one from each parent. So if we take 5B5DC14 as an example commit here, we can see that it actually has two parents, and therefore it actually represents two sets of diffs. One diff from 5B5 versus 63A, and another diff of 5B5 versus 2A1. Now, when you do the merge, you won't always get a merge conflict, but you will get a merge conflict if both commit histories modify the same lines in the same files, and we'll talk about this in detail later in the course. So the most important thing to understand about Git, and if you only take one thing out of this course home with you in your brain, this is the slide to take. The commits and the parental relationships in Git fully define the structure of the repository, and sometimes I'll refer to this as the tree. So in this course, we're going to show relatively simple trees for the purpose of demonstrations, and it'll look like this. And you can see that the dots here just represent there's more history above here, and down here there's more history below here. But I'm going to use the term tree and repository interchangeably throughout this course. And just know that these Git repositories that are used in real software development projects can have thousands of commits. So for example, last time I checked, the Linux kernel has over 170,000 commits. And I've said it before, but I'll say it again. All of the interactions with another remote that happen through push and fetch are simply filling the gaps of their or your repository respectively. This is the fundamental basis of all Git, and super important to understand before we talk about more advanced mechanisms like branches. So when you want to inspect the repository tree, meaning look at the history, you want to be using the command git log. I mentioned this before, the newest commit is going to be on top and the oldest commit is going to be at the bottom. If you look at the output of git log, you will notice that merge commits list two parents in the output. I'll show you an example of that in the upcoming exercise. So git log is your friend when you're trying to understand information about commits in the tree. Now, when you run git log at a command line, the tree appears to be linear, it's collapsed, but really the parental relationships are still there, and you can actually tell Git to draw those relationships visually by using a couple extra flags to git log. Those in particular are graph, and if you use --1 line, it'll actually collapse it so that it's more easily viewable in a small terminal window. So just a few shortcuts that I have found useful about git log. It has other useful forms here. Git log by default will start at head, which is wherever you happen to be checked out, but you can give it any ref, and you can say basically start git log at a different location in the tree. You can also do git log and then give it a path to a file in your repository. This will only show you commits that actually touched that file, and it will ignore other commits. You can actually combine these two arguments and say both of these things, meaning start the log at this ref and only show me commits that have touched the file that I give it. And in this case, I think this is optional, but you can give it this dash dash separator, and that's basically just telling Git that the thing on the left is a point in history and the thing on the right is actually a file path. Sometimes you have to tell Git explicitly whether you're referencing a point in history or a file, because you could imagine it's actually possible to create a file that looks like an SHA-1 identifier, in which case Git would get confused on what you're talking about. Another super useful argument to git log is dash dash stat, which will list the touched files in any commit. So if you quickly want to see, oh, for my last few commits, what files did I touch, you want to use git log dash dash stat. Okay, so it's time for the first exercise here. So if you're going to do the exercises at home, go ahead and pause the video here, because in the next few seconds I'm going to go ahead and do it myself and then talk about the results that you should have seen. Okay, so I flipped over to my terminal here. You can see that I'm in my home directory, and the first thing we want to do is actually clone the repository from GitLab. And we do it through this command. We basically say git clone this repository. And we've specified the HTTPS protocol here. If we were using SSH, it would look slightly different. Both GitLab and GitHub have drop downs, so you don't have to even remember these commands. You can just go there and say, oh, give me the SSH command or give me the HTTPS command. Hit enter and you're good to go. So let's run it. You can see that it's cloning the Hello World repo. And then when it's finished, I can cd into my Hello repository. And you can see that I now have a working directory. And if I look at git log, we can see our head commit. Now, when you first clone a repository and type git branch, you'll notice that you're automatically on the master branch. And that is because the master branch is designated the default branch. Now, this is a setting that can be changed in GitLab on a per project basis, but usually the master branch is the default branch if it exists for a project. Now, if you run git branch-a, this is basically saying, show me all branches, not just my local branches, but remote branches as well. So you can see that the star means we're checked out to master. But this repository also knows about all of these remote branches coming from GitLab. Even though we don't have a local branch called any of these, they exist in our history and we can build content off of them if we choose to do that. So if you hit Q here, it'll take you out of this view. Now, when we run git log, most git commands, and this one is no exception, will operate on the current branch that you are checked out to, which remember is, if I scroll up here, the master branch. So if I run git log, we're going to see the commits where head starts at the location of the master branch, which we can see is labeled right here. And we also see that there are other remote tracking branches that happen to be located at the exact same commit of D8481. But we don't really care about those for this demonstration. You can see that this commit is actually a merge commit, and you can tell because it says merge right here, and it says which parents are the parents of this commit. So this commit D8481 has parents 3EDA and 3609. So remember, that actually looks like this in the tree. There's a merge commit and it has two parents. And since it tells you what the merge commits are, you can actually traverse the history and get the information for those commits if you wish as well. So we can see one parent is 3609. You can see that commit is right here. And the other commit, 3EDA, is also in the history. We just have to scroll down a little bit to find it. Here it is. So it's important to note that when you look at git log, look at this, it looks to be linear. If you're not paying attention to the fact that merge commits exist and those parental relationships are explicitly called out here, it would be easy to just assume that every commit on top is newer than every commit below it. That's not necessarily the case, because in order to show all the information here, it has to be collapsed down into a text view. So one way to actually visualize the tree is to give it more information, and we can do that by running git log with -- graph. And -- one line isn't strictly necessary, but it makes everything a little more visually pleasing. So let's go ahead and try that. So now when we show the Git log, we actually see the parental relationships visually. So this is the same commit that head was on before. But now, unfortunately it spans multiple lines here, so really this star is supposed to be right above these two lines. You can see that this star is connected to 3609, that's one parent, and this star is also connected to 3EDA, which are the exact same commits that we saw previously. So the last part of the exercise here is to just show that you can do this on multiple branches. So it's going to default to head, which we're currently checked out to master when we don't give it an argument. But if you do give it an argument, it's going to start the Git log at that location. So let's go ahead and try again. But this time we will give it the location origin dev. Now we're looking at the remote tracking branch called origin dev, and we can see that it's at DC59. We can tell visually that this is not a merge commit. Why? Because there's one commit behind it, and there's one commit behind that, and one commit behind that. And what that means is that this set of 4 commits is a linear set of commits, meaning each one only has one parent. So when you're looking at Git log with the graph view, it's easy to be tricked by what you're looking at. So I just want to point out here at the end of the exercise that it's easy to misread this. So if you look at this area in the circle here, you can see that 354A00E, which is this commit, is not a parent of 7557, even though they're right next to each other as shown visually in the tree. You got to make sure to always follow the lines to the star and then read the commit SHA-1 number. So what that means is that the parent of 7557 is actually, follow the line to the star, is 096D. Okay, so we spent a lot of time talking about commits, the repository, and parental lineage on purpose. We're going to shift gears slightly and talk about Git tags, and then we're going to talk about Git branches. So a Git tag is a super simple concept. It's basically assigning a human readable label to any particular commit. So for example here on the right hand side, if we wanted commit 5b5d to be referenceable by the name v1.0 for like version 1.0, we can create a Git tag at this exact location. So a tag is essentially a constant pointer to a single commit. This tag will always point to this commit. Now they have to be uniquely named. We can't have 2 tags called v1.0. If you try to create a second tag of the same name, it'll error out. Tags are typically used for this type of thing, marking a state of code associated with a release, but you don't have to use them that way. There's actually 2 types of Git tags. There's annotated tags and non-annotated tags. Really the only difference there is the ability to add a description to the tag itself. So if you want to do a simple non-annotated tag, they're also called lightweight tags. This is how you do it. Basically, if you're checked out to commit 5b5d, all you have to do is type git tag v1.0. That will create a tag at this location. So if you wanted to create an annotated tag, you can see the notation here at the bottom where you give it the -a flag, you give it the tag name. In this case, we call it beta7, just as an example. And then in -m, you can actually, between quotes, give it the message that you want to be associated with the tags. If you need to include a verbose description of what this tag means to your project, you probably want to use an annotated tag. If you're just trying to label a particular commit with a short name, you can use a non-annotated tag. So some of you out there may have noticed, and I hope that you did, that we really haven't talked about branches yet. This is purposeful and antithetical to every single other Git tutorial I have looked at myself. In my opinion, understanding the commits and the parental relationships and what a tag is a necessary prerequisite to talk about branches. So I think we're ready now. We're going to deep dive into branches here for a little bit. And it may seem a little weird at first. I want to introduce you to the concept of branches by asking some particular questions to make you think about what a branch is. So let's go ahead and jump into it here. Now, if you do a Google image search of Git flow or Git branches or really just Git, you're probably going to end up with a lot of these images showing up or something similar to these images. And if you notice here that they're often drawn with tracks. Like, it's difficult to see, but this top track's called master. And then that is supposed to be the master branch, and the commits are on the master branch. And there's hotfix, release, develop, feature 1, feature 2. And a lot of these things show these tracks as being branches. In my opinion, all of these images are poorly drawn, and to be completely honest with you, they're wrong and they're misleading. And I honestly think that the reason people don't understand branches is because when they're first introduced to it, they see this and this is wrong. And so let me explain to you why it's wrong over the next few slides here. So I have a confession to make, y'all. I used Git for an entire year before understanding fundamentally what branches are. And I think it's because, you know, there's an alluring concept to branches. It seems so simple that it actually doesn't really need to be discussed, or at least that's what you think. So, for example, when you're first introduced to Git, people say commits are made on a branch, and a branch is defined by the commits on that branch. Because it appears to be so simple, we rarely will consider some of the most basic fundamental questions about Git branches. For example, the question, what is a branch? Can you define it? If so, how would you? What does it mean to merge a branch or delete a branch? And so I like to do this as sort of a visual thought exercise here for when I'm training people in Git, and to ask this question with this visual here on the right. For this commit tree, circle the branches. And I encourage you to pause the video here because I'm about to give it away. So be prepared to be frustrated. This was a trick question and I apologize already. So the question is, in this commit tree, can you circle the branches? The answer to that is no. And so your immediate reaction to that is probably, well, hold on a second, aren't the branches highlighted in green and orange? And the answer to that is no. And then you might also be thinking, well, surely there are some branches here, yes? And the answer to that is no. So without any more information than we have over here, we actually can't circle a single branch, nor can we determine if one exists at all. If you're confused, that's okay. Hang in there with me. I'm taking you down this path on purpose. In my opinion, a lot of the confusion with Git is about how things are drawn incorrectly and that the right questions aren't always answered. So if we look on the left here, you'll see a lot of images, like in that Google image search, will show that branches are drawn this way, where we see, okay, master is on the left track and a branch called green is on the right track. And this implies that branches are comprised of commits. Now this seems pretty intuitive because we can easily distinguish between the commits on this branch. It's pretty straightforward that these are green commits and these are master commits. But consider this, here's the same repo on the right after master merges with green. A new merge commit is created, highlighted here in red. Which branch is it on? Is it on the master branch or is it on the green branch? If you're having trouble answering that question, that's okay, stick with me. In fact, if we take that image that we had on the previous slide and just move it over here into the lower left, you can see that these two commit trees are identical, master and green. I've just chosen to draw the merge commit either on the left or on the right. So the new merge commit seems to not really be on either branch definitively. Then if you ask another question, it gets even more confusing. What if we were to delete the green branch here? What would that look like with respect to the tree? If commits are indeed on a branch, then deleting the branch should delete the commits on that branch, right? Well, what about this one that we didn't quite understand if it was on the master branch or the green branch? Does that go away too? And so as soon as you start asking these questions, all of this breaks down and you start to realize this can't be right. You know, green's content was merged into master. We couldn't have lost those commits. Every commit is retrievable for all time, right? We've already established that. When you start asking these questions and you have a fundamental understanding of the commit tree and parental relationships, all of these hard questions basically disappear because this is not at all how branches work. And the confusion associated with branches, in my opinion, stems from two major issues. One, poorly drawn commit trees. For example, this is incredibly misleading, showing that a branch is along a line here and implying that this commit is on this branch. And like I just said, number two, when you assert that branches are comprised of commits, It's easy to think that because it makes sense intuitively to someone that is new to Git, but it is completely wrong and super misleading. So like I said before, most Git tutorials get this wrong. In fact, a lot of them don't even talk about what a branch is fundamentally because they want to skip the more complicated details in the interest of getting people up to speed. A lot of people say, just give me the commands to run so I can do my job. In my opinion, that's a really poor way to go about learning Git because if it doesn't bite you immediately, you are going to run into more intense confusion later, I guarantee it. So now that we've broken the assumptions of all other Git tutorials and we've asked the right questions, let's talk about what a Git branch actually is. So a Git branch is not a string of commits. It is a mutable pointer, meaning a pointer that can change to a single commit. One way to think about it, and that's why we talk about tags first, is that a Git branch is like a Git tag, but it's a tag that can move. How does it move? Well, when you create a commit, it moves. You can actually, there's other commands like reset and rebase, which we'll talk about, that also moves the pointer. But when you start to think about Git branches not as a string of commits, but as a Git tag that can move, all of these complicated questions just basically disappear and it starts to click. And my goal is to give you that light bulb moment. So if you look over here on the left, here is a more accurate portrayal of how branches work. We're showing through opacity that both Git branches green and master have existed at locations of earlier commits. You can see that green used to be here, then a commit was made. Now it moved, and then it moved here. After commit was made here, green moved here, and the same happened for master. So remember, a branch is just a tag that moves when you make a commit on it. And because it's cumbersome to show where a branch used to be, we don't actually do that at all in Git. So what we do is we only show where the branch is at its current commit. A branch is just a pointer to a particular commit. That's it. Master is pointing to this commit. Green is pointing to this commit at this instant in time. So I want to reiterate that you never want to draw branches this way because this will only confuse people that are new to Git. So now that we have a new definition for a Git branch, let's ask those same hard questions about merge commits and branch deletion using this new definition. Okay, so I've highlighted at the top the most important thing here. A Git branch is a Git tag that can move because that is super important. So let's go back and look at our commit tree with the master branch and the green branch drawn in this way. Now let's assume that we're checked out to the master branch. So on disk we have the files associated with master. We've done a git checkout master, so we're there in our workspace. Here's what the merge and the delete of the green branch will actually look like. So we're checked out to the master branch. If we run this command, git merge green, we're telling Git to merge green into master. What happens when we do that? Master, which used to be here, the branch, meaning the pointer to this commit, moves to the newly created merge commit. Notice the green branch isn't affected at all. Green is still pointing to the commit it was before the merge. Why? Because we merged green into master. We didn't merge master into green. Now let's consider the branch deletion that we were looking at earlier. If we wanted to delete the green branch, remember the question was, are we going to delete the commits on the branch? But remember, a branch is not comprised of commits, right? So when we delete a branch, we don't have to worry about are the commits disappearing. The branch is just a pointer to a particular commit. So when we delete the green branch, here's what it looks like. The command is git branch-d and then the branch to delete. And what happens? The tree remains identical to what it was before. The pointer called green pointing to this commit simply disappears. So just to reemphasize here, when we merge green into master, master moves to the newly created merge commit, and when we delete the green branch, this moving tag just disappears. There's no confusion on branch or commit ownership, and 0 commits are removed as part of this process. This is the most important thing you will ever learn about branches. If you understand that a branch is just a pointer to a commit that can move based on actions you take, all the other complicated bits of Git just seem to fall into place. Now, let's do a similar thought experiment where we have our same repository before we've done anything, master pointing here, green pointing here, and we're checked out to the master branch once again. Let's see what it would look like to delete the green branch before it's merged with master. So if we just execute git branch-d, which is the delete a branch command, give it green to delete green, this is what happens. The green pointer just disappears. Were you expecting these 3 green commits to disappear as well? If you're new to Git, you may have expected that. But deleting a branch does not actually delete any of the commits in the repository. Commits get deleted as part of a garbage collect, and we're going to talk about that here in a minute. But it's important to note that when you do a git branch D and delete a branch, all you're doing is plucking that pointer off the tree. The commits still remain, at least in the short term. Now, for those of you that are a fan of the matrix, you may start to realize the downstream consequences of digesting the red pill here. You'll start to realize that branches only exist for the humans. Git doesn't actually need them. Meaning, you may have run across this if you've used Git before, that if you're not on a branch, Git will tell you, hey, you're on a detached head. All that means is that you're checked out to a particular commit that no branch exists on. That's actually okay, and you can make commits off of a detached head as much as you want, and you can merge with commits referencing their SHA-1 number. Branches and tags are mostly there for humans to keep track of what they're working on. With respect to Git, they simply exist to define which commits to keep on a Git garbage collect. A Git garbage collect will remove commits that aren't reachable from any branch or tag. We'll talk about reachability here in a minute. But that's really all branches and tags are used for from Git's perspective. Another thing you'll realize is that fast forward merges, you may have seen this before when you type git merge, you may see a printout that says merge made by fast forward. That is exactly what it sounds like with respect to the tree. No new commit is created. Remember how when we created merge commits before, we actually create a new commit that has 2 parents? If a merge is fast forward, that commit doesn't need to be created because all the commits reachable from one branch are already reachable from the other destination branch. And in this particular example, where foo was a branch that was located here and bar is a branch that was located here, if you're checked out to foo and you git merge bar, foo just moves from here to here. There's no need to create a new merge commit because there's no divergence in history between foo and bar. In other words, foo fast forwards to the location of bar in this example. Another downstream consequence of understanding what Git branches are is that you realize there's no precise record of where a branch has pointed in the past. Remember, in this visualization, we showed that master used to be here, and green used to be here and here. That information actually doesn't exist anywhere in Git. I've just shown it here as an illustrative point. Since a branch is just a pointer to a particular commit at any point in time, we can't actually know where any particular branch pointed at an arbitrary time in the past. So one thing that's interesting to note in this example with foo and bar, where foo fast forwards to bar, is that there's multiple ways to do the same thing in Git. So in this example, if we're checked out to foo, these commands are functionally equivalent. If we were to git merge bar, foo will fast forward to the location of bar, which is this commit. If instead we were to git reset hard bar, we're basically telling Git, hey, I don't care where foo points now, reset it to make it point to bar, which would also take the pointer of foo and move it to bar. Okay, so now that you have a thorough understanding of how branches work, we're going to do a quick exercise here where we create a branch, delete the branch, and then restore the branch, which is a thing that a lot of people that are new to Git would find very helpful. We're going to use the same Hello World repo that we cloned from GitLab in the previous exercise, and we're going to create a new branch at whatever the location of our current branch is. So we're going to type git branch to observe our current branch and then create a new one called my branch at that location. So So if I flip over to my terminal here, I'll just run a git status real quick to show you that we're on the master branch, and you can see that if I type git branch as well, same information is shown in git status, and you can see that we're up to date with origin master. This just means that our local master branch points to the exact same commit as the remote reference of the master branch coming from the origin remote. Now if we want to create a new branch at this exact location, what we do is git checkout-b, we'll call it my branch. This is a name of your choosing, and when we do that, we create the new branch and immediately check out to it. Now you can also create a new branch using the git branch command, and if you run help, you can go through all these man pages and see that there's a million ways to do everything. I like to use git checkout-b because it creates the branch and switches to it at the same time, which is useful. Now if I type git branch, you'll see that I have two branches, and the star means that I am checked out to my branch. Now we're going to make a commit here, which means we need to make a change. So let's choose just the readme file. We'll open it up. You can see there's only one line in it, and we'll just say, hey, Dan was here. We'll save the file, close it, and git status will show us that we have a modification. Now, if we want to create a commit, we're going to have to git add it here. So git status is your friend. It will always tell you what your options are if you just read the information that it's giving you here. So if we want to add this in the next commit, all we got to do is git add readme.md. We'll notice that git status has now changed the coloring to show green, which means that it's in the changes to be committed section, aka the index. And we're going to go ahead and git commit-m and just give it a commit message right in the command line. So the message I'm going to give it is updated readme by Dan. We hit that and a new commit is created. Now if we check git log, you can see here it is. Here's the exact message, and here's the new commit that we just created. You can see that it's head, which is coincident with my branch, both of which pointing to this commit. Now if we run git log with the graph option, and decorate isn't necessary, depending on your git version you can include it. I think it's on by default in this git version. It'll just show the branches associated with the commits. You can see that we have one commit, which is a linear commit ahead of D848, which is exactly where master was. So our new branch called my branch is one commit ahead of master. Now I'm going to copy off this commit SHA-1 because we're going to need it here in a second. So what I'm going to do is just open a file called sha1.txt and just paste it in here so I can get to it later. As an aside, you can see that Git's found this untracked file that doesn't match any git ignore pattern, so it's just telling us that. That's no big deal because we're going to get rid of that file. It's temporary anyway. Now let's go ahead and try to delete the branch. Now we're on the branch we're trying to delete, so check out what happens here. If you do git branch-d, which is the delete command, and you say my branch, it'll say cannot delete branch, and that's because Git by default will not let you delete a branch that you're currently checked out to. So let's go ahead and check out to the master branch and try the exact same command. In this case we're going to get a different error. Git's saying the branch my branch is not fully merged. If you are sure you want to delete it, run git branch-D. So this is just Git warning you that if you delete this branch isn't merged into any other branch, which means that the commit that we made, meaning this commit that we stored off, would essentially get abandoned and would eventually be garbage collected. But let's go ahead and do it anyway. Git branch-D, my branch. We're forcing the deletion of this branch, and it says exactly where it was. Let's pretend that you accidentally deleted this branch and you didn't want to, and there was real work on it. You want to be able to restore this branch. Well, in order to do that, all you need is the commit hash associated with where the branch was. Now, we happened to store it off in this file, but if you didn't store it off, you can actually get to your most recent commits by looking at git reflog. So if you run git reflog, you'll see the most recent commits that we were checked out to. And right now we're checked out to the master branch, right, because we switched branches. But you can see that before that we were checked out to this commit. So you can always use git reflog to look at your recent history. If you're worried, well, how do I find the commit on the deleted branch? You can use git reflog to do that. And now that we have this commit, we can actually restore the branch by just doing a git checkout-b, my branch, and then this optional argument here will tell you where to start the branch. So if you don't give it an argument here, it's just going to start the branch where you currently are, which in this case is at the location of master. But we're going to give it this extra argument and say start my branch at this exact commit. And when we do that, you'll see that git branch is showing we are on my branch. And if we look at git log, we will see 1214. So we just restored the branch that was forcibly deleted just a few minutes ago. So what I want to point out in this exercise is where in the repo tree a branch is created is crucially important. And it's one of the things that trips up people new to Git pretty often, which is that when I create a branch, where is that branch? Well, it's going to be created at head, which of course is the commit you're currently checked out to, unless otherwise specified. So like I mentioned, this git checkout-b command will accept an optional extra argument, which is the location of where to start the new branch. So this can be any ref. Now a ref in Git terminology is just a point in history. So you can give it the actual commit hash, you can give it a valid tag, a local branch, even a remote branch. So you could say origin/dev or whatever you want here. As long as it's a point in history that Git understands, then that is considered a ref. Thanks for watching, everybody. I hope you enjoyed this portion of the course. In total, it's about 2.5 hours long and contains 8 exercises that I perform along with the viewer. Like I said at the beginning, check the video description for coupon links. I'm Dan, the Git School Dude, and I'll see you guys next time.